You know, every single time you open your browser, you are placing your trust in a 40-year-old system that is, no exaggeration, the absolute cornerstone of the modern internet. So today, we're going to pull back that curtain. We're talking about DNS. It's the invisible engine that makes your entire digital life possible, and we're about to find out exactly how it all works.
Oh, we have all been there, right? You type in a web address, you hit enter, and nothing. Just that spinning wheel of death. Now, you might blame your Wi-Fi, you might blame the website itself, but a lot of the time, the real problem is hiding in plain sight, in a place you can't even see.
See, every single time you click a link, it kicks off this incredible invisible journey across the entire internet. The success or, the failure of that journey and how fast it happens is what determines whether you actually connect to where you're trying to go. And right at the heart of it all is a system called DNS.
So what is DNS really? Well, the official manual calls it a hierarchical distributed database, which sounds super technical. But honestly, the easiest way to think about it is like the internet's phone book. We as humans remember names, like example.com. Computers, they need numbers, IP addresses, to find anything. DNS is that absolutely crucial translator that makes the whole conversation happen.
Okay, so to really get a feel for DNS, we're going to follow a single request on its journey. I mean, from the very second you hit enter to the moment that page pops up on your screen. Let's trace the path of a DNS query and see all the stops it makes along the way.
All right, here's the roadmap for our little trip. It all starts right there on your own device with a quick check of your local caches. If the answer isn't there, the request moves on to what's called a recursive resolver. That's the server that does all the heavy lifting. From there, it has to ask a root server, which is basically a directory for the entire internet. That root server points it to the right TLD server, think .com, .org, whatever. And finally, the TLD server points to the authoritative server, which holds the prize, the actual IP address.
So that first big stop is the recursive resolver. The best way to think of this is like a super helpful librarian. Instead of you having to search the entire library yourself, you just walk up to the librarian and ask. They're the ones who go and do all the hard work of tracking down the answer. And this is key. They remember that answer in their cache. So the next time you ask for that same website, the librarian can just hand it to you instantly, no searching required.
After bouncing through that whole hierarchy, the query finally reaches its destination, the authoritative name server. This is it. This is the source of truth. It holds the official, definitive record, the IP address for the domain you're trying to find. It has the final say, and it's that answer that gets sent all the way back to your browser.
Now that caching I mentioned a second ago, it's a massive deal. It basically creates two totally different kinds of queries. You've got a cold query, which is when that resolver has to make the full, long journey we just described, hitting every type of server. But then you have a warm query, and that's where the magic happens. The answer's already stored in a nearby cache, and it comes back almost instantly.
And just look at the difference this makes. A warm query that's already cached can take less than 10 milliseconds. A cold query, doing that full round trip, we're talking over 100 milliseconds. Easy! That's a tenfold difference. That is a delay you can actually feel when you're waiting for a website to load. This is exactly why caching is so fundamental to a fast internet.
So, knowing how a single query works is one thing. But how do big companies and organizations build out their DNS infrastructure so that it's not just fast, but also secure and super reliable? Well, it all comes down to smart architecture. Let's take a look at how the pros do it.
A professional setup looks a lot like this. Instead of having just one server trying to do everything, the best practice is to separate all the different DNS functions into logical layers. You've got your internal network, then you've got this firewalled buffer zone, often called a DMZ, and then you have the external internet. Each one of these layers has servers with very, very specific jobs.
Now you might be looking at that and thinking, okay, that seems a little complicated. Why go to all the trouble of having separate servers for caching, that recursive layer, and separate servers for holding the actual records, the authoritative layer? I mean, why not just put them on the same box? Well, it turns out there are some really, really powerful reasons for keeping them apart.
Really, it all boils down to resilience. For one thing, if an authoritative server goes down, a separate recursive layer can just go ask a different one, and the user on the other end never even knows there was a problem. This separation also protects against human error. Let's say someone accidentally deletes a vital record. The cached version can keep things online while you fix the mistake. And on top of all that, it just makes everything way easier to manage, troubleshoot, and scale.
And maybe most important of all is security. That public-facing authoritative server,
It is a prime target for attackers. By keeping it completely isolated from your internal network and your caching layers, you're basically creating a virtual air gap. This setup ensures that even if that external server gets compromised, the attackers can't get into your core infrastructure.
Okay, so a great architecture gives us a solid foundation for reliability and security. Now, let's build on that and focus on the one thing every single user cares about: performance. How do we make these queries as lightning fast as humanly possible?
Here is our target. According to performance experts, a really high-quality DNS query should finish its job in under 50 milliseconds. That is the benchmark that separates a great user experience from a sluggish, frustrating one. So, how do we get there?
Well, there are quite a few tools in the toolbox. You can start by choosing a provider that has a fast global network of what they call points of presence. You can carefully tune your cache settings. Browsers can even prefetch DNS records for links on a page before you even click them. And of course, just placing servers physically closer to your users is always a huge win. But one of the most powerful techniques out there is something called Anycast.
Anycast is just a brilliant piece of network magic. It lets a whole bunch of different servers, spread all over the world, announce themselves using the exact same IP address. Then, the internet's own routing system just automatically figures out which of those servers is closest to you from a network perspective and sends your request there. It's almost like having a local copy of the server no matter where you are in the world.
And the benefits here are just massive. You get way faster responses because you're always talking to a nearby server. You get incredible redundancy because if one server fails, traffic just automatically reroutes to the next closest one without missing a beat. And it even helps with security by spreading out the traffic from a massive attack across the entire globe, which seriously dilutes its impact.
So we've gone from a single tiny query to global architecture and these really advanced routing techniques. Let's kind of bring it all home and talk about the big picture. Why should you actually care about all the nuts and bolts of DNS?
It's because a fast, well-designed DNS system is literally the bedrock of a good digital experience. It is not just about shaving off a few milliseconds here and there. It is about building an internet that's resilient to failure, that's secure against attacks, and that's smart enough to handle the incredible scale and complexity of our modern world. It is, truly, the invisible engine that powers all of our connected lives.
And that kind of leaves us with one final big question. DNS is a foundational protocol that has been with us for decades. As the internet just continues to explode in complexity, with new devices, new demands, new threats, how is this old system going to continue to adapt and evolve? That is the challenge for the next generation of the internet. Thanks for joining us on this deep dive into the heart of the web.